Hello, everyone. Welcome to our presentation today. I'm Russ Wolfinger from Jump R&D, and I'm really pleased to be joined by my friend and colleague, David Barnett from Syngenta. We're really excited to talk with you today about a relatively brand new application of Jump and Jump Pro using and analyzing images. It's kind of a new direction for us within Jump that we're very excited about. And I remember we spent a lot of early COVID years working on a brand new add-in for Jump called Torch Deep Learning, which we had been hearing from a lot of customers about interest in this kind of thing. And as you know, there's been an explosion worldwide with interest in AI and ML and deep learning. And probably the two most popular packages out there these days are PyTorch and TensorFlow. And we kind of settled in on PyTorch, and it turns out Torch has a nice C++ interface that we were able to tap into at a low level. And so we've been able to put together a nice add-in that seamlessly integrates with Jump Pro. And we put it out there. And I remember being excited. I think it had only been out a few weeks. And somehow David found out about it. And David, I think you were one of the very first ones to take a look at it. And I remember hearing about your early successes. And so really happy today to kind of hear your story and how things came about, and also some applications and kind of where things stand for you now after having been able to work with these kind of data and applications over the past few months. So David, let me pass it over to you now, and hear about what you've got going.
Okay, thank you, Russ. It's really good. Um, so, sorry, just got to share my screen. Okay, hopefully everybody can see this. Okay,
Yeah.
so yes, so thank you, Russ, for that. So this is, yeah, as Russ said, I saw this quite early on in one of the early adopter programs, and it's something that we've wanted to look at for quite a while on the image analysis front. And I'm just going to explain the story behind that on our high throughput system that we've got. So a bit of blurb about the company or the agribusiness, that it is a growing concern about how we're going to feed the world in the future. So by 2050, there's going to be approximately 9 billion people, and the requirement for the food is going to increase much more than that. So as a business, we are looking to grow more and more. And Syngenta on its own has about 30,000 employees over 90, I think it's more than 90 countries. And we've got quite a big sales there. So nearly 17 billion 3 years ago. The largest R&D site that we have, and it's the one that I'm based at, is at Gellets Hill in the UK. So it's just outside London. And we spend a huge amount of money on research and development within the company. And we have all different types of chemists, synthetic, computational, analytical. I sit in formulation chemistry, which is basically putting all of our knowledge together and selling products. The formulation trends that we have, because of regulatory pressures, cost pressures, and the speed that we have to get things to market to, as I said, about all the regulatory pressures that we have to make safer products, means that the complexity of formulations is growing exponentially, nearly. And we have to make things safe, not only to manufacture, but to also for the farmers that use our products, and also for the consumers who buy the products which our products are used on. So because of this, we saw a huge opportunity to use automation to do a lot of the background work for us. As I said, because of the complexity of the formulations, the complexity of the composition, so what actually goes into the bottle, has increased a lot. And the processes behind that, so the order of addition as well, is also, or can be, very important. And the responses that we have, so whether it settles within the bottle over time, whether it thickens over time as well, often are non-linear because of the different things that we have to put into the bottle. The rewards that we saw, a larger, more complete data set, so therefore hopefully actually understanding the products that we sell to the farmer better. It also can reduce the repetitive nature of the work that we have to do in the laboratory to get our products to market. And we can also build in some things around about the cost as well. So if we can buy our materials cheaper, we can sell our products either cheaper to market, or we can make more profit from them, which is usually the way, I must admit. And also the improved product performance. So we can build in things, some adjuvants, as we call them, to actually help things get either into the plants or into the insects better. And because of the complexity, this is just a very simple explanation of the number of components that we can put in there. So if we have, top row, we have 20 ingredients and we just want to do a one-to-one blend, that's 190 samples. And a formulation chemist could do that in the lab. If you want to build in more complexity and just do a straight one-to-one blend, that's 1,100 samples. And that isn't something that a formulation chemist can do in a reasonable amount of time. You can see if we've got more and more number of ingredients, we can get to nearly 2 million samples, and we're not going to get anywhere near that in the lab. So a few years ago now, about 15 years ago, we invested in what we call Artemis, which is the formulation high throughput system at Gellets Hill. And there you can see the kind of scale that we were working on. So this is something which can make the samples and also characterize the samples automatically. And the system can make about 200 samples a day and characterize them fully as well. So a step change from what the formulation chemists can do in the lab. One of the tests that we have to do is to see how the sample would react when it's poured into a spray tank. So we use a standard test, standard industrial test, which we call into a crow receiver. So we make up normally a 1% solution in that, and we have to manually check how well that's bloomed. So when you pour it straight in, how does it bloom? And also the stability over a number of hours. So it can be up to 24 hours that we have to do that test. So again, it's a very subjective test. One chemist might see that it's fine. Another one might be a bit more discriminative and actually see that there's a bit of, say, cream up the top of the sample or a bit of sediment down the bottom. And here, a bit small, apologies, as an example of what we're looking for as the outputs from. And this is all very visual. So on the left, we have the best samples, still not brilliant, but it's very good. Going from left to right, it goes on to bad. So basically, your sample is then dropping straight to the bottom of the cylinder and there's no dispersion at all. So if a farmer was to put this into a spray tank, then they would, without any agitation, then it wouldn't be sprayed successfully onto the field, so therefore onto the plants. So on Artemis, going back to the beast, we have a visual analysis module, so VAM, which is probably the strongest aspect of the characterization of it. So what it does, it takes a number of pictures. I'll give you a demonstration. I'll show you the image in a minute, using laser backlight and front light from it, and it's all contained within a nice shiny box. And this is an example of what we have. So this is one sample, and we have in blocks of 3. We've got different exposure times. So first 3, there's a front lit, back lit, and then a laser which comes in into like a plane into the sample, into the front, and you're seeing what's reflected back. The second 3 is a different exposure, but again, it's a front lit, back lit laser, so coming into a plane like that. And the third section is again the same, a very long exposure time, and you can see that the intensity of the color tends to increase as you would expect with longer exposure times. The next block of 3 is the laser coming from the back, so you're seeing what's actually detected by a camera from the laser. Again, it's a plane of a laser coming through. So down the bottom, you see some very little red dots, and that's what's coming through the sample. So it's not quite as opaque down the bottom. The one on the right-hand side we tend to ignore because it doesn't tell us anything at all. Hopefully that was clear. This is one example. This is a creaming sample. So if you look at the images, you tend to see a white bit across the top on the left-hand side of block of 3, and it's quite clear on the backlit that there is something up top. That's what we term a creaming sample, and what we're looking for is a homogeneous sample through all of that. And what we currently have, and what we've had for a number of years, is something based on a program called ImageJ, and it gives us a numerical value of the sample, and it doesn't really care what the sample is. It just gives us a numerical value back. So anything from 0 up to 255 is one of the numbers for color. So we get red, green, and blue as an example for that. We do not get a human readable output from that. So it's very much up to the individual, normally myself, to actually put all these numbers together and tell the chemist what the sample is. So is it a good white homogeneous sample, which is the ideal, or is it a sedimented yellow sample? So as part of the numbers, we can get the color, but it's quite time consuming to do that. What I've wanted for a number of years is a program that can actually tell me what a sample looks like. So is it a good white homogeneous sample? So I wouldn't have to interpret anything at all, maybe a few checks in the background, but I wouldn't have to go into the laborious nature of the numbers. So as part of this, we did a design of experiment to actually screen out a number of emulsifiers from that, and also get then the images back that we need to work through all this torch information, and also some other reasons as well. So we've got a number of samples. So we had about 800 samples that we had to prepare for an experiment, which we used for this image analysis. All the images were prepared in triplicate. The image analysis was prepared on each of these samples as well. So there are actually in total 7 images per sample, which I then went through and did my own interpretation of them. So whether it's a sedimented sample or cream sample, whether it's homogeneous, whether there's a bit of foam, various different things on there, which I hope you can imagine was quite time consuming to do. So we had over 6,000 images to do, to look through. It did take quite a while to do that. I didn't get it right first time, probably still not quite right, but I tried my best on this. There are various samples I took out for various different dosing reasons. Images are retained for any other technique you may want to do. When you look at a sample in the lab, your analysis of that is basically disposed of straight away, because you just pour the sample down the sink and you can't look at it again. With any images, it's there forevermore. So what would we use to do this image analysis? Well, this is a thing called torching jump, so that's quite good. And I'm sure Russ will go into more details, but this is basically saying that what Russ has just said anyway, that this program can actually look at an image and interpret it for me based on some prior knowledge, which I've put into there. My laptop, which I do all of this on, is a high spec, and I would highly recommend you get a high spec PC for this, because it does use a lot of memory to actually perform this. I'm not going to do anything live here because it can take quite a while to do it, especially in the more intricate type of analysis. And but I have a number of examples where I can see slight differences. So we are honestly about to get onto the good stuff. But as a caveat to this, I'm not an expert in this at all. I I know what the numbers mean when they come out, but how it works, I don't really know. And I've got a quote there from Socrates, which I was quite proud of when I found it. I know that I know nothing about this. So I'd leave it up to experts to try to explain it to me. And even then, I'm still a bit, oh yeah, okay, right, okay, yeah, fine, I'll leave you to it then. I'm also only showing very simplified work. I've done a lot more work in the background to do this, and the data will be supplied to you as well. So hopefully you'll be able to look at that and get some even better information out from that. As I've said before, the results aren't perfect. I'm happy with an 80% correlation between what I think the samples look like and what JMP says it looks like. I'm getting far more, higher than that. There are other tools available to this. You can actually use the Python script in its native environment. And what we have thought about doing is actually putting this as part of our Datanesis pipe work, sort of pipeline. So we will be hopefully putting this in as an automated type of thing once we've got more knowledge and more confidence in what this, what the outputs really mean and that they are true. So we are nearly there, honest. A few thank yous before I go on to the good stuff. So we've got various thank yous there. A few people from JMP, Liz Easton from Janet's Hill, who looks after all of our JMP licenses, and Alan Brown, who some of you may remember, who's a retired statistician at Syngenta, who's been a great influence on using JMP at Syngenta over the past few years. As I say, he has retired now, but his legacy lives on. So hopefully I'll be able to get on to JMP. The design of the experiment, which I'm not really going to go into, is across the top here. So we have, there is a simplified version. So we have the AI system, 3 emulsifiers, and that's the amounts there, those 3. The solvent there with the levels applicable to those there, which make up nearly 1,400 samples. We have 3 different types of cuvette, which is what we prepare the samples in. So we have the neat cuvette, which is the neat sample. We have dilution, which is about 5 minutes after it's prepared and inverted, the image is taken. So that's a t=0. Then next day, so after approximately 24 hours, we want to see how stable these samples are over a number of hours. The visual analysis and the color are my interpretation of them. So there's homogeneous, which is the ideal situation. Cream, which is where the sample's risen to the top. Neat, which should always correlate with the neat cuvette. Sediment, which is where the samples have sedimented to the bottom. There. He says, I'll find it in a minute. And foam, where your sample's been inverted and it's created foam, which isn't an ideal situation for the samples. And as part of the torch add-in, you can actually make k-fold columns. So as Russ's recommendation, we have 3 columns here, which are basically the validation columns across there, and the image snips. So they're not the full resolution images. Put into the data table there, and you can see there are, I hope you can quite clearly see, there are different qualities of sample in there. As I said before, I'm not going to run through this because it can take quite a while to do. Hopefully you can see a number of analysis that I have actually done previously. So the main figures that I look at are these ones here, the training R² to the validation accuracy. And as I said before, I'm looking for about 80% agreement between what I've said they are and what the model say they are. And you can see up Here you've got like 96%, 97 there. So there are some very good correlations in there. There are loads of different types of image models you can go through. The lower you go down this list, the longer they take. But I have tried a number of these in the past, and I found that this LeanNet 5 is actually a good compromise. So between the speed of the analysis and the actual outputs, so you can get better as you go down the list, but only very slightly. And I am very happy with the 95% we've had there. You can also alter number of layer sizes, the batch size, and the image size as well. Again, I'm not an expert. I just fiddle around with these numbers and get different outputs. And you can see I've tried a few here, and there's no great improvement over the default, which are this top one here. And one of the very many nice things is you get this plot here about the training history, and you can see that what you're looking for is it to come down a lot lower, potentially quicker there, and you can click through different models to see how they perform against each other. So you can get some really good ones there, and you can also get some so-called suboptimal ones which are very noisy. You can improve them, but you got quite a lot of noise out there, but you can improve them as go along. Another thing that I quite like looking at are these plots here. So you can actually see what kind of probability you've got of getting a correct answer. Although it may look quite messy, the actual numbers that it's not predicting correctly, and again, this could be that I haven't interpreted properly, there's only 33 there out of about 1,500. So actually very good correlation there. And as a proof of that, you can also look at the confusion matrices here. So it's getting most of them correct. Yellow against yellow is 100%, one there. So as you may expect, you can detect different colors if you want to. And white is at 97%, and very good correlation there against the validation as well is also very good. And you can try different models there, and different regions. So sediment, and it's not very good at predicting foam. It's not an important test. And cream, that's not predicting great confidence, about 84 out of 1,500. So not too bad. So this is actually showing me that there is a lot of confidence behind this, and we can build this into our workflow for analysis, so it can automatically, hopefully, pick up the image, do its analysis, and tell us what it looks like in a human readable form. Again, it's very basic testing. We can put a lot more information into this if we needed to, different colors. So we can put in blue if we have blue formulations as well. So that's a very quick, basic run through of my my playing around with a torch add-in for Jump, and it's been quite fun actually. And for more information, don't come to me, go to people like Russ, who can actually give you a lot more information. So over to you, Russ. I'll stop sharing.
Thank you, David. Wow, that such an impressive example. Really exciting to see, especially too, since I know you're an expert formulation chemist, but you're not a deep learning expert, but you're able to get in there and get some results. This is exactly how we've designed the software, and even Jump in general, designed for scientists and engineers, and now like engineer data scientists are kind of a new thing coming down the pike. I wanted to mention too, technically, it looks like, if I'm not mistaken, David, that LeanNet default model is also resizing your laser images to be 28 by 28 pixels only. So kind of fairly strong reduction in resolution. And I have seen examples actually where that tends to really degrade performance. In your case, it's pretty impressive.
It's working really well. Yeah.
So, but for other applications, there's the flexibility to like use bigger images, which will slow things down computationally, but sometimes it's well worth the trouble. That's where those NVIDIA GPUs on Windows can be very handy. And I echo your recommendation. You need some decent hardware to run these models. Fortunately, they're fairly affordable, at least on Windows now, thanks to the gaming world. They often use the same kinds of chips. If you can get the problem is if you got teenagers or something, you may be fighting over the machine. Um, but it's really fun to see the application here, David. Congratulations, and I'm looking forward to working with you more on these applications. And I think in a way we're kind of just getting started. I wanted to mention a couple additional things to kind of build on what you were talking about. First of all, and just so that folks are aware, we're going to be doing a second presentation that'll be complementary to this one. And depending on when you're watching this video, it's 2024. If you're watching before October 17, there's still time to sign up. If you want to watch live, go to LinkedIn and you can find this advertisement if you want to go to my page or Alexander Beck and sign up. If it's past October 17th, I think you can likely still find the recording to see some more details, and we'll be going into more depth on a couple of topics too, kind of as a follow-on to the presentation today. I also wanted to mention that this is not just an isolated example. For example, this paper was just published this year from a group. These are researchers from Singapore and Cambridge and BASF, and they've got this nice paper on shampoo formulations and kind of very similar aspects where they have a nice design of experiments approach, which we love within JUMP. This is just right in our wheelhouse, kind of experiments and analyses that we like. And then they take pictures of their formulations, and again try to build classifier models to do that. And they've got also some of these nice automated robots that help collect the images as well. So it's really great to see this. And I think this tech, we're able to really leverage the capabilities of this high quality data now and get the most out of it. And thankfully, this they actually made their data public. And here's just a quick view of it. And we were able to run. We also ran this through the Torch add-in, these images to build a classifier, and we were even able to improve a little bit on the results published in the paper. So there's a lot of room, I think, with these models. They're pretty incredible what they're able to do. They're not foolproof, and sometimes they even make silly mistakes. For example, here, I think this was a case where it really helped to do cropping. You've got to be careful about artifacts around the edges of the images, and sometimes the models, they're so kind of greedy. Sometimes they'll focus in on aspects that are not what you want. So in this case, we did some cropping up front, and then we're able to get really nice results. So if you'd like to give the add-in itself a try, it's available on the JUMP community for free. If you just do a search, maybe the easiest way would just be to do a web search, Torch Deep Learning JUMP Pro. You should be able to find this page, and you do need a working copy of JUMP Pro 18 or 19 early adopter is also available now. Either one of those should work. And then you just download the add-in here and you're good to go. And to make it even more compelling, we've got a nice collection of examples put together now called the Torch Storybook. And this is actually, just a JUMP table, which you can even download even without the add-in just to take a look if you want. Where we're up to 47 examples now across a bunch of different types of applications. It does tend to be a little bit of a focus on chemistry, which is one of our, probably arguably our most important industry or emphasis in field of science, including, for example, this one I thought might be kind of the next build on where we've got here data from, this was actually a paper from Discovery Europe last year, maybe earlier this year, in a fermentation batch process. And they actually had time data. And the interesting thing here is we were able to build images from this data using JUMP Graph Builder into a heat map, and then pipe those into the Torch Deep Learning. So kind of something you may not have thought about at first. And in fact, if there's maybe one theme today, it's that this idea of fitting images within JUMP with deep learning models, it just kind of opens up a whole brand new venue and just all kinds of different applications. A lot of the applications in this table are from images, but I wanted to mention also we're doing unstructured text For example, using SMILE strings of molecules to predict properties, pretty incredible. And I hope to talk about that more in a different presentation, but just wanted to whet your appetite. And please feel free to take and download this table and look through examples that might catch your interest. Check them out. The table is set up with links where you can download the data, all of which are public data sets. There's also example outputs and references background. So if you want to get up to speed quickly, this table is designed to help you do that with a bunch of really nice examples. Always good to learn by example. So anyway, we're very excited about these applications, and I'm hoping David, as we go along, folks will be able to kind of follow nicely in your footsteps, and we'll tune in for other applications that we've got. So thanks again, David. I really appreciate the chance to work with you on this. And so, what are you thinking, David, for next steps with your analyses?
It's about trying it on different samples and ensuring that everybody is happy with the results that we get. It's kind of building on the knowledge we already have.
Very nice. And I know we also have customers who are already they've kind of done the same thing, and they're actually starting to deploy their models in practice. A lot of them are using Python, and we've got applications now where you can say train models in Torch, save it as a PyTorch object, and then load it into a Python program using Jump's Python integration many times too. So we've got nice connections to that now. So a lot of exciting things happening. Just a way to do this really kind of, this is what I consider kind of standard non-generative AI ML, very popular and practical. And in your case, David, maybe that might be saving you some trips to the optometrist and really accelerating and improving your workflows and day-to-day activities.
Oh, definitely, yes. Yeah.
All right. Well, thank you everybody for tuning in. We hope to see you at the discovery meetings or other chances we get. Do feel free to reach out to us any way you can, LinkedIn or Jump email. We'd be happy to talk with you further about all the exciting things going on with this and other things going on with Jump Pro.